Today we are going to continue our chemistry lessons. So today we are going to speak about equilibrium and equilibrium constant. So first of all, let's draw some kind of graphic. So yes, this one. So this is the product. No. This is the reactant. And this is the product. This is the concentration, and this is the concentration in this time. So as you can see from this graph, in the initial rate of the reactants was very high, but after some time the reactants became zero, which means that the concentration of reactants became zero, which means that the reaction has 100% of conversion. It means that all the reactants have become products. So as you can see, this is the common reaction. But today we are going to talk about another reaction which called reversible reaction. The form of graph will remain, but we will change these curves. So and this one. This is the reactant and product. Products. So this graph makes differ from that graph because in this case we have no 100% of conversion. It means that in this point there is in this state this reaction remain constant. It means that the concentration of reactants and products became constant, and this is called dynamic equilibrium. What is dynamic equilibrium? Dynamic equilibrium occurs when the rate of reactants and the rate of products are same. So forward reaction, this reaction, and backward reactions are opposite and they are same. In this case, we reach the dynamic equilibrium. So there are some tips there are some reminders of this equilibrium. First of all, this kind of reaction is reversible. Secondly, in all the time, reactants and products are present. So the concentration during the time will remain constant, and there is no change, but it doesn't mean that it's stuck in the middle. It continues. This is this reaction continuing, but as I said before, backward and forward reactions are opposite and equal. So that's why dynamic equilibrium occurs. So as an example of dynamic equilibrium, we can say this kind of formula. So as you can see, propanol, ethanoic acid, gives us propyl-ethanoate and water. So about this reaction we'll talk further in further time. So what kind of conditions can change the equilibrium? So we are going to consider 4 factors. First of all, it's concentration. Secondly, it's temperature. Thirdly, it's pressure. And fourth one is catalyst. So, what can you say about these 4 factors? So, let's begin from the simplest one. First one is concentration. Looking at this reaction, we can also, if we increase the concentration of a product, consequently it will shift to the left. And reversible process, if we decrease the concentration of reactants, the reaction will shift to the left, and if we decrease the concentration on products, reaction will shift to the right. It's very easy to understand, and let's go to the second part. So the second, let's consider pressure. Temperature will be the third one. So when we talk about pressure, we are talking about gaseous molecules. For example, let's take Haber process. So in Haber process, so it's very significant industrial process. So nitrogen plus hydrogen gives us ammonia. So this is 3 and this is 2. Yes, so something like this. So in this case we are talking about gases. So as you can see, in this part of reaction we can see that there is a coefficient of nitrogen is 1, but we don't write it. The coefficient of hydrogen is 3, and here we have the coefficient of 2. So here is a 1 plus 3 is 4 and 2 is 2. 4 is, of course, is bigger than 2, and if we increase the pressure, so the equilibrium will shift to that part of equation where we have a fewer molecules of gas. It means that if in this case we will increase the pressure, the reaction will shift to the right. And if we decrease the pressure, consequently it will shift to that part where we have more molecules of gas. So yes, that's very important actually. So and one important thing, that if we have like equation where on the right side and on the left side we have same amount of molecules, if we decrease or increase pressure, there won't be any changes. So that's the point. So let's talk about temperature. Temperature, in fact, temperature is the most complicated thing in this kind of processes. First of all, if we have exothermic reaction, exothermic reaction, which means that when the reaction occurs, there is a release of energy. Actually, it is with minus in this case. And endothermic reaction. When energy is absorbed. So, in this case, in exothermic reaction, when the energy is released, if we increase the temperature, the reaction will shift to the left. Yeah. For example, here is A, for example, plus B, and C plus D. So, minus energy release, exothermic reaction. So, in this case, if we, as I said before, if we increase the temperature, the reaction will shift to the left. And if we decrease the reaction, the temperature, the reaction will consequently shift to the right. In endothermic reaction, this process have an opposite effect. So, if we have a plus, energy absorbed, if we increase the temperature, so it will be shift to the right, and if we decrease the temperature, it will shift to the left. So yeah, that's very important. And the last one that we're going to talk about is a catalyst. So catalyst. In fact, catalyst does not affect the position of equilibrium, but it is very significant in big industrial processes. As I said before, Haber process, here we have an optimal conditions, and to reach these optimal conditions we need a catalyst. As you know, catalyst decrease the activation energy of reaction, and so that's why we need less energy to overcome this barrier, this energy barrier. So you know this graph very well. For example, this is the peak of reaction, but catalyst divide these two peak into this one. So we need slower energy for each step. So very significant thing. It does not affect the position of equilibrium, but it affects to the rate of the reaction, which leads to the creating of optimal conditions in big industrial process. So that's very important.
So how we can describe the value of Kc or Kp? So let's describe the value of Kc by this reaction itself. So Kc will be equal to product of concentration of the products. It's like multiplying the concentration of propyl ethanoate and multiplying it to concentration of water. So concentration of CH3OOCH C3H7, concentration of propyl ethanoate multiplying to H2O concentration and dividing it to reactants multiplying concentration. It's equal to concentration of propan 1O OH multiplying to concentration of ethanoic acid. So, as we know, the concentrations units are mole per decimeter cube. and concentration itself describing by this parenthesis, and units for concentration is mole per decimeter cube. So, as we know from this reaction, the Kc at this rate doesn't have any units, but it depends on situation. Somehow, in some situation, we can have 2 reactants or more and can have 1 product. And by this rate, the value of Kc or Kp is changing by number of reactants or products. So, I think it's not so important now. So, the value of Kc is depending to number of reactants and products. Affecting factor for Kc, as I said, is only temperature. So, some students are mistaken by the combining the definitions of Kc or rate constant, but it's not right actually, and Kc is affecting by the 1 factor, and it's not affected by catalysis or concentrations changing or pressure. So, let's talk about one simple chemistry principle, which name is Le Chatelier's principle. This law states that when a change is applied to a system in dynamic equilibrium, it changes the reaction tries to oppose the change effect. So somehow, if we want to change the condition state of this reactant, we're adding this reactant, and somehow the reaction itself opposing the change factor. So if we boiling up the water, the reactants will try to push it or oppose from the change. So let's talk about this reaction. This reaction is very important for today's lesson, because this reaction will be our first video practical work in chemistry lesson. And so we're adding propan 1-ol, the alcohol itself. Name of this reactant is alcohol, and ethanoic acid is carboxylic acid. We'll talk about these compounds or organic compounds later. So this product is naming by ester, and it's simple to know that it's water. So the reaction itself is very slow. Even we use as a catalyst the concentrated sulfuric acid, H+ here, and as we know that from arrows, the reaction itself is reversible chemical reaction, and it attends by 2 parts. First part of our practical work will be involving the preparing of reactants for reaction. So we said that practical will include part 1 and part 2. So why are we doing that? Why we don't combining the 2 parts for 1 day, and why we don't why we can't do this experiment now? Because we can describe the disadvantages and the advantages of this reaction, and one of the disadvantages of this reaction are the reaction is very slow, and because of that we must wait a week to fully complete this reaction and this practical work. And because of that, we're having second part of this practical work. So advantages of this reaction are like, if we're like waiting for a week, we can ensure that we're having a completed equilibrium solution, the solution in equilibrium state, and we preparing the reactants at first part, preparing. In second part, we using titration reactions, and we will talk about this reaction later. So by the we must at the first part of this reaction we must prepare reactants, and first of all we must prepare 5 centimeter cube of alcohol in boiling tube, 5 centimeter cube of carboxylic acid in a second boiling in the same boiling tube, and we must add to the mixture the 2 centimeter cube of sulfuric acid, because sulfuric acid is, as I said, is concentrated, and it is a catalyst for this reaction that changing the rate of the reaction. So, let's talk about the general formula for every equilibrium constant value. So, value of Kc is let's like make an example of the reaction. A B is equal to C, and D is equal to D. So the little numbers A, B, C, and D are concentrations, like coefficients of concentrations. So all of them are coefficients of reactants and products, and Kc value will be described as A in the power of A, B in the power of B, little b, and C in the power of little c, and D in the power of D. It is a general formula for all reactions, reversible chemical reaction, that includes equilibrium shifting.
So today we are starting a practical part of our lesson, and first of all let's introduce some equipment that we are going to use in this experiment. So as you can see, this is the pipette. So it's the simple construction with 5 milliliter in it. We need exactly this volume of our acids and reactants. So if you are going to describe this part consists of 3 main parts. So for this is labeled as E. It means that, from word empty, it means that if we push it with something in this ball, it will just split. And this button called S, it means suck. It means that you are sucking the reactants for this pipette. And this is labeled as A. We are by pushing it, for example, we just remove air from this ball. And this is a simple construction.
So then what we must do, how we can start our experiment. First of all, we must place 5 centimeter cube of our reactants, and at first place it's ethanoic acid, as you can see. So we're taking exactly 5 centimeter cube of our first reactant. Yeah, it's much, so
yeah, That's all.
So from menisc we can see that it's exactly 5 centimeter cube of our ethanoic acid, and so we place this value of reactant to our boiling tube. So we're pushing E button to make pipette empty and placing our reactant to boiling tube. So, secondly, what we must do, Aytvar?
So, second thing that we should do is taking another reactant and do the same function, yeah, the same thing. It's too strong.
It's too sharp smell, and
Yeah.
because of that we are closing it.
So we are taking an ethanol. Yes, alcohol. And adding the same volume of it. As Madhyar did, we are measuring from menisc, exactly from menisc. Yes. Please close it.
Yeah. And the third thing that we are going to do, we are going to place 2 milliliter of our catalyst, and at our state it is 1 mole decimeter cube sulfuric acid. So we're opening this tube and taking another pipette to fully absorb it. So we're taking exactly 2 centimeter cube of our catalyst, and we're pushing this button, and then exactly 2 centimeter cube of our catalyst, we're placing it to our boiling tube to change the rate of this reaction, as we mentioned in our introduction. So as you can see, pipette is
Could you please?
empty. Yeah.
So we are carefully shaking this mixture to make sure that all of them are mixed well, because for our reaction it should be mixed well, consequently. It's obvious.
Yeah.
And Madhyar, for what time we are going to leave this?
We're going to leave this boiling tube for a week to ensure that the mixture itself reached equilibrium position.
After a week we are going to do our second part.
Titration.
We don't talk anymore.